Students, what's up with my background? It's white and not magically green. What's up with that? Well, I wanted to share with you some information today prior to our lab, and I needed to show you some things without the green screen. So that's the answer why. Earlier this week, we've talked about waves. And some of those waves we discussed included sound waves like this. Sounds cool, right? And we played around with sound waves when we made our string phone. Remember our string phone? And some of you had the opportunity to really play around with our string phone. And we explored how sound energy, the waves of sound or sound waves, travel through the string from one cup to the other. But as we've said, water waves and sound waves require something to travel through, whether it's water or a solid material or even air. Electromagnetic waves, however, can travel through the vacuum of space. In our lab activity this week, we are going to be doing something called spectral analysis. As we mentioned in the previous lesson, spectral analysis is like detective work for astronomers because we use spectral signatures or the fingerprints of different elements with a luminous body, meaning a body that's giving off light, and using a spectroscope, whether it's a simple spectroscope or a more complicated spectroscope, we can rip or stretch that light apart into its fundamental portions of the visible light spectrum in order to identify the exact wavelengths of light, the spectral signature of the different elements. So with our spectral analysis lab today, here's what we're going to be doing. I have a device here, and let me go up to a larger screen so you can see it. Here's a device, and inside this device are glass tubes. And these glass tubes are filled with an element. And this device enables us to send electricity through the glass tubes and energizes the element in a gaseous form with electricity so that it becomes a luminous body. So during this activity, we're going to have the lights off so that we can see the luminous body better as we use our spectroscope to make our observations. Now, what are we going to observe? Well, with a full spectrum, in other words, like sunlight that we might examine or the lamp light that we'll see as soon as this video is over, we're going to see a full spectrum of colors, Roy G. Biv. We're going to see the Roy G. Biv, a full rainbow of colors with full spectrum light, such as the light that comes out of the lamp that we're going to start off with. And we're going to be drawing the full spectrum of colors using our colored pencils, going from Roy to Biv, Roy G. Biv. So red, orange, yellow, green, blue, and violet, all of the colors of the rainbow. So that's going to be our starting point. Now, from our starting point, we're then going to examine the luminous tubes, which represent the spectral signatures of specific elements. And we're going to see something a little bit different. We're going to see only specific wavelengths of light illuminated instead of a full spectrum of colors. And you'll get an opportunity to see that when we use our spectroscopes here in just a moment. You're going to see a fingerprint of different elements because each tube is filled with a different element. And so you're going to illustrate the fingerprint or the spectral signature of each element according to the wavelengths of light that you see. And you will compare that with the full spectrum of colors in your observations. Now, once we've examined all of the individual known elements, you're going to have a series of spectral signatures that might look like these. Of course, yours will be done much better. And then I'm going to give you an unknown element. I'm not going to tell you what the element is, other than the fact that it will be one of the ones you've already seen. So the unknown element, you're going to compare that spectral signature with the ones that you do know. And based on the spectral signatures, you should be able to identify the unknown element. And this is how astronomers can do laboratory tests with known elements here on Earth, because they're the same elements everywhere in the universe, and then hook up a spectroscope to a telescope, examining a star far, far away, and be able to identify unknown elements, even though we're separated by enormous distances. So that's the idea of our Spectral Analysis Lab here today. But before I sign off, I just want to explain to you how the spectroscope is used. So I'm going to zoom back in here so we can see a little bit better. And let me explain the spectroscope to you. First of all, despite the fact that it looks very simple here, please be careful using these. They are precision instruments. Only hold the spectroscope in the middle of the spectroscope. There are opposite ends. One end has the diffraction grating, and you can see that rainbow appearance, the Roy G. Biv, when you are looking at it on the screen here and when you look at it with your own eyes. If you recall, the diffraction grating is a piece of thin plastic with millions of little prisms engraved into it. So don't touch it. If you touch it, you can ruin it and it won't work. This is the end that you're going to be putting next to your eyeball. You are going to be looking through the side of the spectroscope with the diffraction grating on it. But don't put it onto your eyeball. That would hurt and that would be disgusting. So it's a little bit further away from your eyeball. Now, the other end of the spectroscope has a slit on it. That slit allows light to pass through. Now, the slit should be positioned so that it is vertically positioned. In other words, going straight up and down. You don't want to position it horizontally. You want to position it vertically. So the slit should be positioned, and I'm trying to get it so that you can see it on the screen. Hopefully you can see, oh, there we go. Hopefully you can see that. The slit should be going straight up and down. The slit is what you will be aiming toward your light source, the luminous body. And since our tubes are positioned vertically in our device, positioning your slit vertically will enable you to see more of the light. Now, these have all been calibrated so that when you aim the slit toward the light source, and then you use your eyeball to look to the right inside your tube, you will see a spectrum of colors, Roy G. Biv. And when we look at individual elements, you're not going to see the full spectrum. You're going to see brighter color bands. It's those brighter color bands that you will be illustrating in your book. And actually, when you look in, I misspoke a moment ago, when you look inside your spectroscope, you're actually going to be looking to the left inside your spectroscope, not to the right. Otherwise, the rainbow is in reverse. So when you aim the spectroscope slit to the light source, just look over to the left inside your spectroscope and you will see the rainbow of colors, Roy G. Biv, and it's the brighter bands that you will be illustrating as the spectral signature or fingerprint of each individual element. Now, if what I've just said to you seems like it doesn't make sense, believe me, it will when you start using the spectroscope and you start looking at the luminous bodies. So have fun being an astronomical detective today with our spectral analysis lab activity. So until next time, I'm going to say bye-bye. Bye-bye.